think about something you know to be true from the past. And then imagine you went out on the internet and you can't find it at all. It's not there.
Now with quantum computers, what you're doing is you're creating basically alternate universes and connecting with the twin particle that has entangled, that's entangled with on the other side, and you're pulling information back from another dimension, from another universe. Now, when you punch holes in our existence, in the matrix, in the veil, whatever you want to call it, once you punch a hole in it, it never goes away. And what are you letting through?
So D-Wave builds quantum computers. The way that they work, if you know how this works, is one of the interpretations is that you tap into these parallel universes and they do computations. Sounds really weird. But what's happened is this idea has been hijacked to describe something called the Mandela effect, which is this thing where the past changes. So think about something you know to be true from the past. And then imagine you went out on the internet and you can't find it at all. It's not there. It doesn't match with your experience. So these people think that D-Wave is responsible, and CERN.
Quantum computers you're talking about. Yeah, I mean, what I would actually say is that I lied to you, and that quantum theory is not a theory of microscopic objects. It's not a theory of small things. It's actually a theory of isolated things. And it's because it's possible to isolate something small like an atom from its surroundings that it behaves in this bizarre manner. But in principle, if we could isolate Fred from his surroundings, at the moment there are air molecules bouncing off him, there's photons of light bouncing off. If we could put him in a vacuum chamber, and we could
do it all the time.
Yeah, and we could completely isolate him from his surroundings, he would behave like a quantum object. He would be able to go through two doors simultaneously and do all these incredible things. And that's, of course, that's what a quantum computer is. I mean, it's an attempt to build something big that is quantum, to exploit the ability of an atom to be in many places at once, to do many calculations at once. And a quantum computer could massively outperform the fastest supercomputers we've got today. But the problem in building these things is they have to be isolated. You've got to build a big thing that's completely isolated from its surroundings. So they're being built, in vacuum chambers, and they're cooled to minus 270 degrees, all this kind of stuff. But there's currently a race on in the world, between militaries, and I don't know if you're building a quantum computer, are you?
We're doing things like that,
Yeah, universities, governments to try and build a quantum computer.
Yeah, no,
so it will. We will have one on a desktop within, maybe 20 years. Currently, we've got kind of primitive quantum computers, and the biggest can manipulate something like about 10 binary bits.
Yes.
I mean, your computer at home can manipulate billions of bits, so they're very primitive. But they're not only a practical nuts and bolts device that you can put on a tabletop that behaves like a quantum object, but they have profound kind of philosophical implications for the nature of reality. Because it's very easy to imagine building a quantum computer within maybe 20 years that can do more calculations simultaneously than there are particles in the universe.
Yes, that's right.
And then you have to ask yourself, where is the quantum computer doing the calculations? I mean, your computer can only do, it can store a number of a particular size because it's got the memory space. Where is the quantum computer doing the calculations if it's using more physical resources than exist in our universe? And David Deutsch, who's a physicist at the University of Oxford, says that what the quantum computer does is exploits parallel realities. It exploits copies of itself in parallel universes. So when you set a quantum computer a problem, it splits into multiple copies of itself in parallel realities. They all work on threads of the calculation, and they come back together again with the answer. So he says the quantum computer is something entirely new under the sun. It's the first thing we've ever invented that exploits parallel universes.
If parallel universes exist.
If they exist. I mean, you see, the interpretation of that double slit, the double slit experiment, where a photon appears to go through two slits at once. I mean, there are 13 possible interpretations of quantum theory. And one of them is what we call the many worlds. So we explain the fact that the photon, the photons appear to mingle with each other by saying that the photon goes through one of the slits and it mingles with another photon that went through the other slit in a parallel reality. And that's one possible explanation, and actually it's embraced by a sizable minority of physicists.
If we first met Geordie Rose and first invested here. He had a 1-qubit machine, and he was waiting for the 2-qubit version to come out, but it hadn't yet. Actually, sorry, the 2 would be here, and this is, I think, 4 on the log scale. No, maybe a 2 on the log scale. Oh, right, that's the 4-qubit there. So the 2-qubit one hadn't come out yet. We invested here, and he said, I think it's going to double every year, number of qubits. So again, logarithmic scale, straight line would be an exponential. But when you add qubits, it's very much unlike Moore's law on that other curve. This is like a Moore's law on top of a Moore's law. It's more like going from a 32-bit architecture in Intel to a 64-bit. It's like a 2 to the n phenomenon, roughly. I mean, there's some derating factors. But it means that it gets pretty weird pretty quickly, which is, if you fast forward a little bit, we currently have machines that they're making that are competitive with class computers. After all this work, it's finally kind of like a laptop, that big black box you saw. But you fast forward just, a little bit, it becomes faster than all computers on Earth. Now again, they only do one particular type of problem. It's not general purpose computing, but it's graph optimization. It maps to machine learning and Monte Carlo simulations and protein folding and stuff. So it's interesting for supercomputing, but here's where it gets really, really crazy. Go forward just a little bit farther, faster than the universe. Now what the hell does that mean? That means if you took all the matter of the universe and reconstituted it into the best computer that Intel could ever design, giving them the length of the universe to work on the problem. So the best theoretical computer that could be built, and you give that universe-sized computer the length of our universe in terms of history, how many, the 13 billion years that we've been around, they still couldn't solve problems that the quantum computer could solve readily. That's mind-bending, and the only physics explanation for how it works is that it basically engages the computational resources of parallel universes. Now that is a point of competitive differentiation you don't often hear in a pitch, to say, Intel's just using this inner universe. Well, how could they possibly compete, right? That's where my head explodes, but I think it's pretty exciting if I give it a 10% chance that it doesn't hit some roadblock like noise or something that makes it fall off the rails, and if it just keeps going a couple more, like Moore's law, just a couple more dots on that curve. They currently are bringing up their first 1,000-qubit machine as we speak.
David, the many worlds interpretation of quantum theory arguably is one of the most remarkable and astonishing claims anywhere in science. You've been one of the pioneers of this, so please tell me what it is and how can you believe such an extravagant claim?
Well, what it is first, it is the idea that the physical world that we see around us, the room, the stars, galaxies, and so on, is just one tiny sliver of the whole of reality. And the whole of reality includes many such objects, many of the kinds of objects that we have traditionally thought of as the universe. And so it's sometimes called the many universes theory. I actually prefer I prefer to call it the multiverse theory because it contains a lot more than just those things that we used to call universes. It contains other structure as well. So the whole thing as a whole, reality as a whole, is the multiverse.
Now, how can you believe such a thing?
The reason we have to believe this, if we believe anything due to science, is, well, really there are two paths that force us to believe that there is a multiverse. One of them is simply to ask of quantum theory, which is the deepest theory that we have as physicists, in terms of which other theories in physics are expressed. We ask, what does this theory say about reality? And it turns out that in the equations of quantum mechanics to express what happens in a process in the laboratory, you have to write out many paths for the apparatus, many different histories of it. And if this is applied to different histories of the laboratory as a whole, of the experimenters, of the world, and so on, then that is the parallel universe's interpretation. Historically, that is why people first believed in parallel universes. I actually prefer a more concrete argument, which is that if you start with the experiments, if you start with a simple thing like the two-slit experiment, where you pass a single photon through two different slits, that's already giving you a hint of the parallel universe's kind of idea, that if you take seriously what happens in that experiment, the outcome can only be explained, cannot be explained by the idea that the photon passed through only one of the states or took any one path. Any one path would give a wrong answer. And the different paths affect each other. Again, if different paths affect each other, that means that different histories affect each other, and so you can build the argument up into many universes.
Now, in your multiverse, the different universes, if we call them that, actually do interact, which is how you generated it in the first place.
Yes, they are in constant, intimate interaction. And although the experiments that can only be explained in terms of multiverse are very hard to arrange, and they require very subtle laboratory techniques. In fact, we know from the theory that practically all of our everyday experience is conditioned by multi-universe interactions. For example, matter couldn't be solid if each atom only took one path. What keeps it solid is the interactions between different instances of the same atom in different universes. That is what makes for rigidity. It's also for what makes permanent magnets. It's also the reason that we can have amplification of signals. It's the reason that we can see stars.
Now, clearly, that is not a common accepted view.
That is, well, I think all physicists who look at these phenomena would agree that quantum theory is needed to explain those phenomena.
Yes, that's
but
right.
they would not express quantum theory in terms of parallel universes.
For example, the solidity of matter could be explained by the exclusion principle, because things just can't occupy the same spot, and so
Yes.
so it seems rigid when in fact it's mostly
Yes,
space.
so that's a good example. So if we take the exclusion principle and express it in its true quantum theoretic terms, it says that a sum of certain terms, of a vast number, exponentially vast number of terms, has to equal some other exponentially vast number of terms. And that is saying that each one of these things, if it represents reality, represents a different history of the atoms, and they are affecting each other.
When you're saying a different history, some people talk in quantum mechanics as though these are possible histories, but they don't have a basis in reality. You are claiming that they have a basis in reality?
Yes.
I mean, this is a dumb question, but how many are there?
There are vast numbers of them.
No, it's not good enough, vast. I want a number.
So, for example, if we're talking about the number of different histories that's happening in, let's say, a cubic meter of air, then we're talking in terms of 10 to the power of 10 to the 23 different histories are all happening at the same time.
So that's 10 to the power of
number one with 23 zeros after.
and that billion, something like that.
Yes.
And so that's the number of different histories of this 1 meter of air. And of course, we have a gigantic universe,
Yes.
so one would take it to unbelievable pattern. Now, those histories, when did they occur? That's from the beginning of time or right now? I mean, is
Yes.
these sequentially or in parallel?
One has to understand it in this way. Well, first of all, yes, they have existed since the Big Bang. There was an older version of the quantum multiverse in which they only appeared
Branching.
as branches, but that has now been abandoned. And in fact, we now think of it in terms of happening for all time. But remember that there's a lot more in the multiverse than just universes. And in fact, universes are an emergent property of the multiverse. So some types of phenomena, like human thought and the outcomes of scientific experiments, are expressible in terms of universes. But a lot of other phenomena, such as quantum computers or the interior of molecules, are not. And for those, it's the multiverse rather than individual universes.
You what, mate?
Yep.